In this video, we're going to talk about how floating point numbers are represented in the IEEE floating point representation. We'll begin by talking about fixed point numbers and then move on to floating point numbers. And we'll talk about single and double precision numbers. We'll also talk about special cases, which include positive and negative infinity and not a number representations. We'll also talk about normalized numbers and denormalized numbers. Let's begin by talking about fixed point numbers. We'll start by talking about decimal numbers before we move on to binary numbers. This will help us get our context and show us what's going on. So here's a typical decimal number, and we see the decimal point here. To the left of it we see an integer value, 123. And each one of those digits has a certain place value. So the 3 is in the ones position, the 2 is tens, and we've got 100. So we know how that kind of number works. To the right of the decimal point, we have the fractional portion. And this 4 means 4 tenths. And this 5 means 5 100ths. And this 6 means 6 1,000ths. So if we look at our base of 10, our place values are 10 to the 0, 10 to the 1, 10 to the 2 as we move to the left. And as we move to the right, the pattern continues, only it's negative. 10 to the minus 1 is 1 over 10. 10 to the minus 2 is 1 over 10 squared. 10 to the minus 3 is 1 over 10 to the third. And so on. So it's a very logical pattern that follows in both directions. Okay, that's what a decimal number is. Now, the same thing goes on with binary numbers. So let's take a look at this number. This is a fixed point binary number, 101.0101. The values of these places are just as we had before, to the left of the, well, we should call this the binary point. We don't really call this the decimal point because this is not a decimal number. We call it the binary point. In any case, to the left of it we have 2 to the 0, 2 to the 1, 2 to the 2. Those are the values of the places, 1, 2, 4, 8, 16, and so on. To the right, the pattern continues in the negative direction. 2 to the minus 1 is 1 over 2. 2 to the minus 2 is 1 over 4. 1 over 8, 1 over 16, and it goes on, 1 over 32, 1 over 64, and so on. Those are the values of the places. So what is this number? Well, we have a 1 here, so we have 4, and we have a 1 here, so we have 1, 1, so 4 plus 1, 5 point something. Well, here we have no halves, but we have a quarter, plus a 16th. Well, sorry, not an eighth, but a 16th. So 4 plus 1 plus a quarter plus a 16th is 5 and 5/16ths, or equivalently 5.3125. So this is the binary fixed point representation of the number 5.3125, or 5 and 5/16ths. It turns out that every binary fraction can be represented exactly with a decimal fraction. Here's an example. 1001.01 in binary is the same number as 9.25 in decimal. And interestingly, the decimal representation will always use no more decimal digits to the right of the decimal point than the binary number has bits to the right of the binary point. So here we have 2 bits to the right, and this number can be represented with a decimal number with 2 digits to the right of the decimal place. And that's true for any binary fraction. On the other hand, some decimal fractions cannot be represented exactly using binary fractions. So here's an example, 0.3. In binary, if we try to represent this thing in binary, we end up with an infinite expansion. in the number is 0.01, 0011, 0011, 0011, 0011, and that repeats forever. In some mathematical notations, we write this number with a bar over the part that repeats. So decimal fractions cannot always be represented exactly using binary fractions, and we should say of finite length. So if you are writing a program that's dealing with decimal fractions like this, you might want to remember that it can't always be represented exactly. Now, one place this matters is with currency. So for example, we might have $7.30. Okay? And we might want to represent that in our computer. But as we see, this fraction of 0.3 is going to give us problems. So we can't represent that amount exactly. So one trick that you can do with numbers is to not represent the dollars, but represent the cents. So instead of trying to represent this as $7, $7.3, represent it as 730 cents. Okay, and that number can be represented exactly. So this is a trick for dealing with currencies and numbers. Don't represent the dollars, represent the cents. Okay, now let's move to the world of floating point numbers and leave fixed point numbers behind. Floating point numbers are an attempt to represent scientific notation. So let's kind of review scientific notation. Here's a number, 123.456. We can represent this in scientific notation as 1.2345 times 10 squared. So we've moved the decimal place over 2 positions. So effectively we divided by 100, and to make it the same number we need to then multiply by 100. Okay, so these two numbers are equivalent. This one, we have a single digit to the left of the decimal place and some fractional portion. And so we're sort of normalizing all of our numbers, so we have the decimal place in a regular predictable place, namely over at the left end. Here's another number in scientific notation, 6.0225 times 10 to the 23rd, which you might recognize as Avogadro's constant. Now, one thing about this notation is that we can represent very large numbers. This number here is just huge. Avogadro's constant is huge. And we're only representing it with a small number of digits, and therefore we're not representing it exactly. So we're limiting the precision. And in this case, we're rounding it to the nearest 10 to the 19th, in fact. Okay, so instead of having a number with 23 places, we've got a number with only 5 digits of accuracy. Now, notice if we put our decimal place here, our leading digit will always be 1 through 9. We'll never have 0. If we have 0, we should move the decimal place over. So we want to adjust the decimal place to where we have a single non-zero leading digit. Okay, that's our scientific notation. We have limited precision, but we can represent very large, and with negative exponents, we can represent very small numbers. Okay, so we trade off precision, and we gain range. We have much larger range. Now let's look at binary numbers. Here's a number, 101.0101, and we're going to move our point, our binary point, over to the left, in this case 2 places, okay, so that we have only a single bit to the left of the decimal place, a single bit to the left of the binary point. Since we've moved it over 2 places, we need to multiply. But here our base is 2, not 10. So we multiply by 2 to the power 2. Now if you want to compute this, we could look at this fractional number and turn it into a decimal representation. It can be represented with the same number of digits, and it turns out to be 1.328125, and 2 to the 2 is 4, and when you multiply these out, you get 5.1325, which is, interestingly, and as you'd expect, when we saw this number as a fixed point number, okay, it was 5.3125. So we haven't changed the value of it by representing it this way. The nice thing about scientific notation is you only need to represent a small number of digits, depending on how much precision you've got, and the exponent. So instead of representing all 23 digits, we can get by with just, in this case, 5 digits of mantissa, as it's called, and a couple digits of exponent. So we can represent a very large number with not very many digits. So it's a very compact way for representing numbers that can be very large and with negative exponents very, very small, without having to waste a bunch of digits just to get the decimal place in the right spot. And the same is true with binary floating point numbers. Now in this case, our leading digit was always a 1 through a 9. It was never 0. The same is true here. It's never a 0, but that only leaves 1. So the leading bit is always 1. It's never 0. So we're going to, in our scientific notation, always put our binary point just to the right of the most significant bit, the most significant 1 bit. Now we're ready to look at the representation of floating point numbers. This is the IEEE single precision floating point number representation. A single precision floating point number is stored in 32 bits, and this is how we store the number. So we've got the least significant bit 0 and the most significant bit 31. These are our 32 bits that we have to work with, and we're going to use 23 of these bits for the mantissa, the fractional portion. We're going to use 8 of these bits for the exponent, and we're going to use 1 bit for a sign bit. The sign bit will be 0 if positive, 1 if negative. Okay? And so the number that we will represent with all these bits will be 1 point, and then whatever these bits are, we've got 23 bits of precision, so a total of 24 bits here. The 1 is assumed. We don't have to represent it. These 23 bits then essentially go right here. And then we've got an exponent, so 2 to the something. Well, with this 8 bits, I'm going to talk a little bit more about how this is encoded, but basically we can have an exponent that's anywhere in the range of minus 126 to positive 127. And finally, we've got a sign bit. The sign bit is either 0 or 1. So this is a fancy way of saying 0 means positive and 1 means negative. Anything to the 0 power would be 1. So minus 1 to the 0 would be 1. So if the sign bit is 0, this term right here, this factor right here is positive 1. On the other hand, if we've got a 1 right here, then minus 1 raised to the power 1 is just minus 1. So this is a minus 1. So this is a fancy way of saying if it's a 0, make it positive. If it's a 1, make it negative. So our number n, if you will, is 1 point and then whatever bits we have here times 2 to a power. And that power can be anywhere between 126 and 127. Minus 126 to positive 127. Now, the bits of the fraction are just copied here directly. Okay, with nothing fancy there. But the 8 bits of exponent encode an exponent in sort of a funny way. This is not encoded as a signed number with 2's complement or anything like that. Instead, it's encoded in this rather unusual way. And so here I'm showing all the 8 bits that could be in this field right here. And two of the bit patterns, all zeros and all ones, are used for something else, and I'll get to that in a second. But the other bit patterns are used for the exponents ranging from minus 126 to positive 127. 0 is represented as, well, this pattern here. 0, 1, 1, 1, 1, 1, 1, 1. So it's not a logical, it's not what you might expect. Okay? It is an encoding, but it's not what we saw with unsigned or signed numbers. It's a different encoding. A bit pattern of all zeros indicates that this number is a subnormal number and it's interpreted differently. I'll get to that. And a bit pattern of all ones means that it's not a number, and we'll get to that as well. But this is what's called a normal number, okay? A normal floating point number. And given that, we can represent a large range of numbers. In fact, the smallest non-zero number that we can represent is about 10 to the minus 38. It's a very small number. And the largest number is about 10 to the positive 38. And we have about 9 digits of accuracy. So we've got a pretty good system for representing lots of numbers in scientific notation. Next, let's talk about how 0 is represented. Here again is the form of a single precision floating point number. 23 bits of fraction, 8 bits of exponent, and a sign bit. Now I said if the exponent was all zeros, it was a special case. And so when the exponent is all zeros and the fraction is all zeros, then we have 0. The sign still matters. So in floating point representation, we have two zeros. We have a positive 0 and we have a negative 0. We'll talk about double precision later, but it's essentially the same idea. We just have more bits for the fraction and more bits for the exponent. But in both cases, we have a positive 0 and a negative 0. And it's either a 1 followed by all zeros for negative 0, or a field of all zeros for positive 0. So with this representation, we can represent both positive 0 and negative 0. I also said that when the exponent field is all ones, it was another special case. So when the exponent field is all ones, we can have several different possibilities. We can have not a number, or positive infinity, or negative infinity. So if the exponent is all ones and the sign bit is 0, note this is a 7, followed by 3 ones here, 4 ones there, and 1 more 1. In other words, 8 1 bits. And here's the same number, only the sign bit is negative. This and the fractional portion is all zeros. This is positive infinity and this is negative infinity. If the fractional part has any bits in it at all, it's considered an invalid number. There's something called not a number. Typically the value we use is FF, which is -1 is a signed number, by the way. But this is a value that's called not a number. It's not a valid representation of a floating point number, and oftentimes we use capital N, little a, capital N for as a symbol for this value, or for one of these not a number values. So what are positive infinity and negative infinity used for? If, for example, you divide the floating point number for 1 by 0, well, you can't divide by 0. But in the floating point standard, as IEEE defines it, the result is supposed to be positive infinity, and the result is positive infinity. Likewise, if you divide -1 by 0, you get negative infinity. And you can also compare numbers to positive infinity and negative infinity. So these are sort of like numbers and sort of not like numbers. They are quantities that can be represented with a single precision or double precision floating point number. Let me talk a little bit more about the not a number thing. So, well, this slide is slightly wrong, okay? If the exponent is all ones and the fraction is all zeros, then we're talking about infinity and the sign matters. So this is not quite right here. If the exponent is all ones and there's anything but zero here, so if it's not equal to all zeros, okay, then we've got something that's not a number. And the typical value we use for not a number is just all ones. So this is the canonical representation of not a number. Canonical representation of not a number. And this is, interestingly enough, this is also as a signed number -1. But of course these aren't signed integers, these are floating point numbers. It happens to be the same bit pattern. So how does not a number arise and what's it good for? Well, there are certain operations. If you divide 1 by 0 you get positive infinity. If you divide -1 by 0 you get negative infinity. But what happens if you divide 0 by 0? Well, it doesn't make sense to be either positive or negative infinity. In fact, it's not a number. So if you perform this computation, the processor will compute a result that is represented with these bits. In other words, not a number. And other operations are designed so that if they are given not a number as one of their operands, it gets preserved. So, for example, if you have not a number and you try to add it to 3.75, the result is not a number. So this allows errors to be preserved. So if in a long sequence of computations something goes wrong, for example 0 divided by 0, then that error is propagated and preserved all the way to the final result. So far we've seen normal numbers, and we've seen positive and negative infinity and not a number. But now I'd like to talk about another special case, which is called denormalized numbers. And in fact, these denormalized numbers include positive and negative 0 as well. So when the exponent is all zeros, we have what's called a denormalized number. The sign bit is the sign bit. We still have a 23-bit fraction. What number is represented by this bit pattern? Well, the sign of 0 or 1 means either positive or negative. In a normalized number, we take the fraction and we put it right after 1 and a binary point. And we have an exponent that's in the range of -126 to 127. Okay? With a denormalized number, when we have this all zeros in the exponent is just taken to be -126. And the fraction is then put behind 0 point. Okay? So the number that's represented with this bit pattern is shown right here. 0 point, and then whatever bits you see, and times 2 to the -126. And so let's look at why this works, or how this works. If you have, what's the smallest number we can represent with a normalized number? Well, if the fraction is all zeros, and we have the smallest exponent would be -126. And with all zeros, the smallest value is 1 times 2 to the -126 with 24 bits of precision. Now let's look at the denormalized numbers, and let's look at the largest value that we can represent. The largest value we can represent is when this fraction is all ones. So it's all 111 times 2 to the -126. Notice that this exponent is the same as the lowest exponent. So the way I think of this is it's sort of sticky. The exponent sticks at the bottom of the range of values. And also notice that this number, 0.1111 times minus 122 to the minus 126, is just a little tiny bit smaller than this number here. This number has 24 bits of precision, so this number has 23 bits of precision. And then if we keep getting smaller and smaller, well, we can't change the exponent. It won't go down any further. We're stuck at minus 126. But the fraction can go all the way down to 0.00001, and that is the smallest non-zero value that we can represent. And notice we had a precision of 24 bits up here, and then we got a little bit smaller and we lost precision. We lost 1 bit of precision. And then as we decline even further, we begin losing precision. And so down here at the smallest value we can represent, we only have 1 bit of precision. And then if we go one lower, we have all zeros. And that's our representation for positive 0. And we can also have negative 0 as well. All these numbers could be negative as well. With the normalized number, there's no way to represent 0 because we have a 1 in there. We always have that 1. But with the denormalized numbers, we get rid of that assumed 1, and that allows us to represent 0, as well as get a few extra numbers in there. Now let's take a look at how the numbers are distributed along the number line. In this example, we're looking at a floating point representation, but we're not looking at a full IEEE single precision number. That would have 32 bits of accuracy, and we'd have just lots and lots and lots of values. Instead, we're looking at an analog, which only has 6 bits. And so our exponent is limited to 3 bits, and our fractional portion is limited to 2 bits. But it shows the same idea that we have with larger representations. And in particular, look at what happens to the values. So here's our number line with 0 in the middle, and we have representations for infinity, which are just shown here, sort of arbitrarily positioned at the right and left ends. And then the red triangles represent the normalized numbers. And notice that they're kind of spread out, and then they get closer and closer around 0. So we have, they're spaced closer and closer around 0. The denormalized numbers are all really close to 0, and we can't see those in this particular diagram. But if we look at the next diagram, we can see how the denormalized numbers work. Okay, so here's our picture again with the same values. Again, we're using an analog of single precision, but instead of 32 bits, we've only got 6 bits. And they're spaced out and they get closer and closer. If we blow up this area right around 0, we can see that our normalized numbers are shown with triangles here. And at some point around 0, we have the smallest normalized number. And then we have regularly spaced the denormalized numbers. So, and then we have 2 zeros. They're shown as separate points here, but they're both at 0. Okay, so this is kind of what's going on when we get close to 0. It's important to remember that these floating point numbers are not rational numbers. They're not scientific numbers. They're not numbers in the mathematical sense. They are, in fact, representations of these numbers that are inaccurate. They're not exact representations of real numbers. And as a result of that, they don't always behave the way you might expect numbers to behave. And here are a couple of examples that show you what's going on, that what can happen. So we've got to be a little bit careful when we use computers to try and represent the real world, because remember, computers are representations of the real world, and the data that is stored in a computer is an incomplete representation, and sometimes you can lose information and it can behave differently than you expect. In the case of floating point numbers, they are commutative. Okay, so this is a property you learn about numbers, that x plus y is equal to y plus x. You also, and that applies when you do floating point addition. It doesn't matter which order you add them in. But you also learn that addition is associative, meaning if you're going to add three numbers, it doesn't matter whether you add x and y first or whether you add y and z first and then add x. But with floating point numbers, we don't necessarily get the same result. So it doesn't follow the associative property that you are expecting to find. And the reason is that due to rounding, we can get some different answers. So let's take a look at this example. Here we have 3.14 plus a very big number, 1 times 10 to the 10th, minus, well, that same very big number, 1 times 10 to the 10th. Okay? And here we do the same thing, only we group it differently. So when we subtract the very big number from the very big number, we get 0, period. And then we add 3.14 to that, we get 3.14, which is what you'd expect. Here, what happens is we add 3.14 to this very, very big number, and because of limited precision, the 3.14 is just lost. It's such a small number in comparison to the 1 times 10 to the 10th that the result of this addition is exactly 10 to the 10th. And then when we subtract 10 to the 10th, we get 0. So the order of the operations can make a difference. The same thing can be true with multiplication. The associative property, which holds for real numbers in the world of mathematics, does not hold for floating point numbers. Also, remember the distributive property. Here we have one number times this minus this. It should equal this number times this minus this number times that. Okay, so this times this minus this times that. Okay. Here we subtract these two numbers and we get 0. We multiply by this and we get 0. Here, when we multiply these two big numbers, we get overflow and we get not a number. And again, we multiply these two big numbers, we get not a number. And the not a number is preserved, so when we do the computation this way, we end up with not a number. So the distributive property doesn't necessarily hold. So far we've talked about single precision floating point number representation. The IEEE standard for floating points also specifies double precision. And in that case, we have 64 bits to work with. What this gives us is more bits for the exponent and more bits for the fraction. But the ideas are exactly the same. We have a sign bit, we have an exponent, and we have a fraction. We also have positive and negative 0, positive and negative infinity, not a number, and the representations are similar. In the case of double precision, we have exponents that range from minus 1022 to positive 1023. And we have, of course, more bits for the fraction. We have the smallest non-zero number being 10 to the minus 308, and the largest number being 10 to the 308th power, with 17 digits of accuracy. So we've got a very large range here, and most numbers can be represented, well, I shouldn't say that. Most numbers cannot be represented in a computer because there are infinitely many of them. But many numbers that you come across in real-world applications can be represented in with double precision numbers. I might also point out that every 32-bit integer can be represented exactly with a double precision number. 32-bit signed or unsigned numbers have only 32 bits of precision. With the double precision floating point number, we have a full 52 bits of precision. And so we are able to represent every single integer, every single signed or unsigned 32-bit integer with double precision floating point numbers, and a lot more as well.